Okay. Good afternoon, everybody. It is a pleasure to have David Bondurant here. This is a live member affinity group event, and in this time, it's joined by not only by Argentina, in the chair of Argentina, but Monterrey, Panama, Puerto Rico and Caribbean, Peru, and Uruguay. In this time, David Bondurant is going to talk us about Geniuses at War, co-branking in Bletchley Park. Bletchley Park is no more than an hour from London. I had the opportunity to visit there. David is going to talk us about what was going on there during the war, before the war, during the war. Code breaking, Enigma is very well known, but he's going to talk more about Colossus. And David is the right person to do that. He's a professional engineer. He worked in the computer and semiconductor industry for 50 years. He was a computer architect at Control Data, Spare Univac, and Honeywell. He was involved with the government-sponsored advanced semiconductor program called BHSIC, Very High Speed Integrated Circuit at Univac. So, David, this is all yours.
Okay, great. We might need to get some people muted. I don't know.
I'm going to do that. Okay, don't worry. Some speakers.
Okay. I'm going to get this off the screen so that doesn't take up room. Okay, I'm Dave Bondurant. I'm coming to you from Colorado Springs today. Buenos tardes, as I was told. In any case, I'm going to talk about Geniuses at War. The title was Bletchley Park, Colossus, and the Dawn of the Digital Age, and it's by David A. Price. And so we're going to basically, and of course, what you see in the background is the Colossus computer, the first digital computer. So here's a picture of the book, which Gustavo showed you earlier. Basically, the book came out in about 2021, and it's about the story of British code breakers from the period from World War I all the way through World War II and beyond. And it's based on classified information that was only released in the 21st century. And so it to me, brought me some new information that I hadn't heard before. Now, this is not my first talk on code breaking. A previous talk that the Pikes Peak Life Member Affinity Group did was about UNIVAC, defense systems, where I worked in the 1970s. And so I worked for UNIVAC, and I was curious about its history. And so I went back and learned that the UNIVAC actually directly emerged from the World War II Navy code-breaking activity of the United States. And it basically continued to develop code-breaking equipment in addition to becoming the leading supplier of standard military computers for the U.S. Navy. And so during that talk that I did back in 2022 on UNIVAC, I had reviewed U.S. and British electronic computer developments during World War II, which included ENAC, Whirlwind, EDVAC, EDSAC, EDSAC-2, Atlas, and Atlas II computers. And so there were quite a number of different computers being developed in World War II and in the immediate period right after World War II. And so most of these developments started in about 1943 as the U.S. was entering World War II. But more recent information from this book that this classified information from this book that I've learned says that the British code breakers started a few years earlier and got there a little earlier than we did, and so in the United States. And so that's what we'll tell you about today is what happened. And so here's a little bit of introduction to Bletchley Park that Gustavo talked about, that's near London. And so the British basically had rivalries within their military services between the Army and the Navy over doing code breaking during World War I. And so they've been at this a while. And so they were doing code breaking even back in World War I. And so these rivalries kind of showed up again in the Americans in World War II, where both the Army and the Navy wanted a piece of the action in code breaking. But Britain basically, in October of 1919, they basically saw the wisdom of combining the code breaking services into a single unit, which they called the Government Code and Cipher School, or GCCS, and it was located in central London. It was being run by the Admiralty, or the Navy, by a guy named Alexander G. Denniston. Now, he had a small operation of about 40 people at that time, because after World War I, there was not so much demand for code breaking. They kind of focused on breaking diplomatic messages just to stay in touch with what was going around the world and what people were saying about them, I guess. In any case, by 1923, this Alexander Denniston was reporting to C, the head of SIS, or MI6 as it's known today, and his name was Hugh Sinclair, and somehow or other he got this nickname Quex. And so Quex, the head of MI6, is using the Code and Cipher School to monitor German developments during, after World War I. And so the Germans, even though they signed this Versailles Treaty, basically started developing a military in the 1920s. And so he's basically keeping an eye on that, even though the Prime Minister, Chamberlain of England, is downplaying the ambitions of the German ambitions in the 1930s. Quex is, keeping an eye on Hitler's aggressiveness and is preparing for the coming war. And so by 1937, the Code and Cipher School started staffing up its staff, and by 1938, moved its operation to a place in the countryside away from future bombs, as they said. But this place is called Bletchley Park. And you can see pictures of the mansion where it was kind of headquartered. And then you can see an aerial view of Bletchley Park today. And so you can see, for example, behind the mansion is a Polish memorial. We'll tell you why the Polish memorial is there in a little bit. And you can see all these numbered huts around the grounds. And so we'll talk more about that. That's where the job was done. And then down at the bottom, you can see the National Museum of Computing. And so Bletchley Park is where the British have put their National Museum of Computing technology. And so you can kind of go and see some of these vintage computers in person today. I haven't been there yet, but I would certainly enjoy that. And so as they expand this code breaking operation, what they're hiring is classicists that have language skills, because that's the way that they used to do it. They did hand code breaking, and it was all about language skills, not about mathematics. And so they weren't recruiting mathematicians at the time. Okay, well, here's a picture of Enigma. And so we've talked a little bit about that. Enigma is a three-wheel German cipher machine that was developed in World War I, after World War I, for commercial use. And so the German military had adopted that machine for encrypted communications as early as 1926. And so they were using that in their military. The military had basically modified the machine to add some more wheels. And so, basically they ultimately had, I think, 5 wheels. And then you can see this plug board in the front. And so they could basically modify the way that these plugs are connected to kind of create some more difficulty in breaking the code. And so the operator would set up the machine daily with the settings from a predefined key list. And so everybody, was setting up their machine the same way around the network. Text was typed into the machine, and the encoded or encrypted text would be output in the lights in the middle. And then it'd be sent by Morse code. And so Bletchley Park was already having difficulty decoding this Enigma code from the Germans. It challenged the traditional code breaking techniques that they've been using during World War I and beyond. And so mathematics were required to unravel its secrets. And so in 1938, they began hiring some mathematicians. So here's why. They basically had visited the Polish code breaking operation in 1939. They hired mathematicians because they observed what was happening at the Polish Cipher Bureau. Question? No, okay. They learned that the Poles had been reading the German Enigma for 6 years. Yeah, any question? Okay. The Poles had trained a group of 20 undergraduate mathematics students in code breaking. And so you can see the names of 3 of these guys that created an analysis of the Enigma signals that enabled them to build a mechanical device to solve it. And so that was called the Bomba. And you can see a picture of the Bomba over here in front of these military officers. Basically, each of these dials, all six of these dials basically were a Enigma machine. And so you could basically run through and test different Enigma settings rapidly to uncover the current setting. And the time, but when they got there in July of 1939, time was running out for Poland. And so in August of 39, Quex, the head of MI6, evacuated the operation in to Bletchley Park. And so they moved on out of London, anticipating the coming war. And so literally a month later, Germany enters Poland and begins World War II. And so what's clear is between them and the Poles, they were getting enough messages through to understand that something was coming up. Okay, well, what happened in Bletchley Park during the war? Basically, they organized teams of people into different huts based upon the type of code that they would handle. And so Hut 6 handled German Army and Air Force Enigma code. Hut 8 would handle the German Navy. Other huts would handle Italian and Japanese codes. And so the Bletchley Park staff would grow to about 8,700 men and women working 24/7 in 20 plus buildings. As you can see on the site, there's just a lot of buildings there. Now, Hut 6 is where the British were decoding Luftwaffe, or the Air Force ciphers. By October 1939, they had figured out how to decode the Italian Navy Enigma by 1940. But the reason they were able to do this was because the German operators made a number of errors in the way they operated the machines. And so they were not operating in a disciplined manner. And so they would figure out a way to break them. But Hut 8, which is where the German Navy was being decoded was that the Navy was much more disciplined, and so it was very difficult to break the code. So enter Alan Turing. Alan was one of the first mathematicians hired by the code breakers. He was born in 1912, showed an interest in numbers before he could read. He went to the boarding school. He was interested in math and science at a young age. He moved to a thing called Sherborne School, an elite secondary school, and then he won a scholarship to King's College in Cambridge. He graduated in 1934 as one of the top math students in his class, and he became a fellow of the college. I'm not sure what it takes to become a fellow exactly, but he was. It sounds good to me. During this time, he attended some lectures on the foundations of mathematics taught by a guy named 38-year-old faculty member named Max Newman. So his name's going to come up a little later here. But one of the discussions in this class was the thing called the decision problem. Could mathematics be used to solve a generally predetermined could a mathematic problem be solved with a generally predetermined process carried out in a mechanical way? And so that's known as an algorithm in today's terms. And so Turing was struck by this conversation. And so by April 36, he had written an article on computable numbers with the application of the Einstein-Dung problem, which is the I guess the decision problem. And so the article describes a theoretical universal computing machine. And so Turing was invited because he's such a stellar student to go visit Princeton University, and there he meets a guy named Alonzo Church, who basically had similarly solved this decision problem. And so they were basically on the same orbit. And then another guy at Princeton was John von Neumann, who's famous for developing the von Neumann machine. And so in 1937, this Church in Princeton is the guy that gives Turing's universal computing machine its name, the Turing machine. So that's where that came from. Okay, well, as soon as the war starts, Alan Turing is basically relocated to Bletchley Park on September 4th. So literally 3 days later, he's taken the train and he's got up there and he's ready to start working. And so Turing briefed on that Polish Bomba machine that we saw earlier, had said about determining how they could overcome its limitations. And so the Bomba depended upon a thing called double enciphering. Basically, they were putting the code in the code, but Turing expected the Germans would fix that error at some point in time, and so he was trying to build this machine to be able to decode even if they don't use that technique. And so he developed a mechanical approach using cribs, they called it, which looked at logical absurdities in the text. This approach reduced the time to find the settings. Now, what he worked with, he basically worked with a British company, the British Tabulating Machine Company. So they were basically a calculator type company that was building mechanical calculators at the time. And they had, basically they designed a Bombay or something, and ordered it by late 1939. And so it's the equivalent of 36 Enigma machines with some additional wiring. And so you can see a picture of the Bombay over there on the right. And you can see a picture of Alan Turing standing in front of it in the movie, The Imitation Machine. And so that's the electromechanical computer that they're going to use to break Enigma. And so even with the Bombay, HUD 8 needed the help of what they call pinches, basically stolen code books or Enigma machine that they could quickly, basically reverse engineer to quickly break the naval code. And so in 1940, the British captured a German vessel off of Norway in its code book. This allowed 5 days of messages to be decoded. It wasn't until spring of 41 when the British captured code books and an Enigma machine from U-110, a damaged U-boat, that they again started decoding. The British captured weather trawlers off of in May and June of that year. And so by August, they were basically decoding messages efficiently and got the time down to about 72 hours, enabling them to read enough messages to turn around the U-boat problem. They could basically track the U-boats and go after them by knowing where they were at. And so this was a key breakthrough. Now the staffs of Hut 6 and 8, though, were frustrated because they still didn't have enough hardware. They were limited by the number of machines, and so only 6 machines had been delivered by August of 1941. In October, the staff was so frustrated they basically got a message to Churchill explaining their problem. Churchill then basically stamped that this program had the highest priority, and so by the end of the war, Britain had built 200 Bombay machines and had them in operation in Bletchley Park. So what's going on over in America at this time? The U.S. Navy, of course, really wasn't on board the war effort immediately. We were kind of staying out of it. The code breaking activity in America was being performed at a thing called Seesaw, or the Communication Supplementary Activity Washington, which was at a facility in Washington, D.C., and the group was also known as Op 20G, and so that's our code breaking activity equivalent to the British in America. A guy named Joseph Desch led the American effort to develop an improved Bombay based upon the British Bombay. And so we're trying to make some further improvements as we enter the program. And so you saw that they've been using Bombay since about from the 1940s to late 1941s in Britain. We finish our design and get it approved in 1942. And so the American Bombay is built by the Naval Computer Machinery Laboratory, or NCML, which had been located at an NCR facility in Dayton, Ohio. And so I would say that that's kind of the equivalent of the British tabulating machine facility at the time. In other words, NCR was building similar kind of mechanical computing devices. So Alan Turing would basically come to America, visit NCML in December of 1942 to see the production, and the first unit was delivered in January 1943. And so it enters the code breaking operation for America, a couple of years later. Initial operations would start in June of 43. A total of 121 of these machines would be built for Op 20G, and the machines would be run by a 3,000 person workforce in the American code breaking operation. Okay, so here we're going to get to the meat of the operation here. I'm going to check. Okay, here you got it. So basically, there's a thing called the Lawrence SZ42 cipher machine that was developed in Germany. And so this was known as the Tunny by the British. And it worked with teleprinters rather than Morse code. And so by the middle 1942, this enhanced version of the machine was being used by the British High Command to communicate to their top commanders throughout Europe. This machine is a lot more complicated to decipher than an Enigma. It has 12 rotors rather than 5, as you can see in the picture. And so just many more combinations of numbers to decipher. And so following the German invasion of Russia, the British start receiving a new kind of radio signal that sounds like a saw. And so they figured out that this signal was a teletype code sent in 5-bit characters. And so that's what this machine's all about, is encrypting these 5-bit characters. The job of decoding this was turned over to a guy named John Tillman. He's the top cryptographer who had been helped break the Russian communist codes following the Russian Revolution. He had also broken 6 Japanese military codes before World War II and the German police codes early in the war. And so he's basically been a busy guy breaking codes. Tillman figured out that the machine had 12 rotors, basically looking at the data. He observed that the data stream had a signal that was similar to a 1919 AT&T patent. And so he learned that the Germans were basically building this thing to the patent, which meant that he learned that they were transmitting a key stream at the beginning of a message. And from this, he concluded that pseudo-random data was being added to the incoming teletype stream to create the encrypted message. So he successfully deciphered one message, that had this key stream in it before the Germans figured out that they didn't want to do that. And so it was back to the drawing boards again. And so in 1941, he turned the problem over to this Bletchley research group headed by a guy named Gerald Morgan. And in October of that year, he handed this problem to a young guy named William Tootie. So here's William. William is another one of these stellar math students. And so he's the son of working class parents. I found it interesting how there was a class structure in England and they make a big deal of it. And so, there was people that were at the upper crust and there were working class parents. And so he basically starts out with a modest background, but he develops an interest in math and science. He won a scholarship to a top secondary school like Alan Turing. He enters college at Trinity College, Cambridge, in chemistry with a side interest in math. He graduated in 1938, continued in chemistry, but he changed his focus to math after he was recruited by Bletchley in the spring of 1939. And so he basically was on board early, and of course ended up in Bletchley as soon as the war started. So Tootie basically was analyzing the messages that were coming in and doing statistical analysis. And so he determined that the size of 3 wheels based upon missing letters in the messages. The research group determined the size of all 12 wheels without ever seeing the machine, doing this statistical analysis. On November 1942, Tootie observed that statistical manipulation of the bits in the message yielded a dot count. And so they basically extracted some data out of the data, the bits that came in, and had this dot count. And the dot count basically would rank order what the best guess was for the wheel. And so yielding that, they could get the settings for the first 2 wheels, and then they would turn around and do this same technique to get the settings for all of the wheels. So this statistical method solved the encryption settings without any special cribs or access to code books. And so it was an algorithm, basically, that they'd figured out. Unfortunately, it was an algorithm that took huge amounts of hand labor to execute. And so it seemed impractical to do it. But another member of that research group, this Max Newman, you remember him? He was the teacher of Alan Turing. He's the guy that taught Alan and that basically stimulated him to define the Turing machine. And so basically Max observed that this statistical analysis just made the problem more interesting. And so here's the details on Max. Max was born in London in 1897, so he's a little older than these other guys. He's the son of a German immigrant and an English farmer's daughter. So at 18, he received a scholarship to St. John's College, Cambridge, in mathematics, but he's sent off to war. So he ends up going to World War I. When he gets back, he goes to Cambridge in 1919 and graduates with distinction, becomes a fellow of St. John's College, Cambridge. In 1937, he's the guy that taught that foundations of mathematics that inspired Turing's paper. As the war started, he's still teaching at the college when a Nobel laureate, Patrick Blackett, who I really don't know, but I think he's well known, recommended him to Bletchley Park. And so following 2 days presentation, Newman recognized that a computing machine would accelerate the solution. He presented a proposal to develop a high-speed machine to perform statistical analysis. So he kind of triggered the development of the first digital computer. He was put in charge of developing such a machine. Alan Turing would not work on that machine, but he would recommend a young designer from the post office, a guy named Tommy Flowers, as the chief designer of this new machine. So here's a picture of Tommy Flowers, who I had, and Gustavo said he hadn't heard of this guy either. I'd never heard of him, but he's another interesting fellow. He's born in London in 1905 to working class parents. Flowers at age 12 won a scholarship to East Ham Technical College. So he, is basically a prodigy if he's moving that fast. He began working on an apprenticeship in mechanical engineering at a thing called the Royal Arsenal, which I don't know too much about, but I suppose that they're building weapons for the military. He then won a 2-year training program with the post office. Now, the post office in England does more than send mail. It's kind of running the telephone system. So as you see, he's working at the General Post Office, developing complex electromechanical telephone switching systems. And he received an electrical engineering degree while taking classes at night while he was working. And so he moved from building these electromechanical machines to the research department, where he became familiar with electronic tubes. At that time, tubes were being used in simple radio systems. So analog communications was used in the network to communicate, things that control the network. And he experimented with tubes for digital electronics. And so he's one of the first people to actually use these tubes as a 1 or 0, a switching device rather than an analog device. So Flowers is recommended to Max Newman by Alan Turing because he worked with Alan in 1941 to try to enhance the Bombi with an add-on tube processor, so a sort of an analog processor to go with that Bombi. And so he figured out that this guy was pretty smart and knew how to do tubes. Flowers concluded that Bletchley Park needed such a digital electronic solution if a system was to be fast and reliable enough to solve the statistical problem. And so in February 1943, he proposed a new machine called Colossus Mark I. Okay, well, it wasn't quite that simple. The battle within Max Newman's shop at Bletchley was on which way to build the high-speed computer. Flowers, of course, felt that electronic tubes could be made reliable enough to build a fully electronic solution to the computer, but it might take a little bit longer to get it done. A guy named Dr. Wynne Williams of the Communications Research Establishment in England felt that tubes were unreliable at the time and would never work in time. And so he proposed a hybrid computer that was built out of analog tube logic, which is just a small number of tubes, and then mostly out of relays. And it would be built by that same British tabulating machine company that did the Bombi. So the Wynne-Williams solution ultimately was the sole solution selected by Bletchley Park. And so that resulted in a thing called the Heath Robinson machine. Don't know who Heath Robinson was, but basically in England, it was considered a kludge, or, it was just a maze. It was too complicated to imagine. But that's why they called it that. And so the Heath Robinson machine, which you can see over the right, is a simpler machine than the ultimate Colossus. And it has two problems. It takes hours to process a message. And because it's analog, it's unreliable. It gets different results each time. And so it worked. By September of 43, Heath Robinson is processing 2 to 3 messages a week. Only a fraction of the total number of messages they're receiving, however, so it's not really solving the problem. So Flowers and the post office are not taking no for an answer. They decide to develop this electronic solution using their own funding. And so they basically start building Colossus Mark I on their own. And so the first Colossus, as you can see on the right, has a paper tape input for the message. And so basically the operators that are receiving Morse code, or the 5-bit machine teletype codes, convert that into paper tape, and that gets fed in at high speed into the computer, a 1500 tube logic unit, configured with switches and plug boards, which is kind of that stuff in the middle, which is, and the switches and plug boards is the program memory for the computer. And then finally, the output is a fast teletype, which is an electric typewriter. And so that's the first fixed program computer. And you'll recall that they're designing this during 1943, and they installed the first Colossus Mark I at Block F Bletchley. I don't know where Block F was, but that's the room that it was in. And so they put it in there in January 18th, 1944. And so when it arrives there are already 3 of these Heath Robinson machines working. And so it takes them about a month to kind of get it up and running. And on February 5th, a trial was fed, trial message was fed into the machine, and it was decoded successfully in 10 minutes, which is 500 times faster than the Heath Robinson machine. That was, electromechanical. And so they would now be able to fully decode all German high command messages. So that sounded great. Churchill got the word, and he demanded that Flowers produce 12 more machines by June 1st, 1944. Kind of a crucial time, as you recall, because and so Flowers basically didn't have the parts basically to build all that stuff that fast, and so he can build one of those before June 1st, 1944. And the team that's working on this kind of got the message that June date was the invasion of Europe, or D-Day. So Flowers, well, they're building that one machine, I guess, starts working on Colossus Mark II. And so Colossus Mark II is going to process the data from those 5 bits of teletype code in parallel. And so he's got a parallel processor going to process each bit of the 5-bit code in parallel. And so the tube count in this machine increases from 1,500 to 2,400. The design of this thing was done by 4 logic designers, a large team of junior engineers to implement the circuit boards, and 70 production workers in Manchester assembling 3 Mark II machines in parallel. And so they managed to deliver the first Mark II unit in time for D-Day. And by October 10th of 1944, 10 of these Colossus Mark IIs have been delivered to Bletchley Park. So in summary, basically, Flowers and Colossus are the first to use binary digital or electronic circuits at scale. So they're, putting lots of them together to build a computer. They're the first to run binary arithmetic and logic at high speed. It's the first synchronous machine. So it's got a 5 kilohertz clock that's driving everything. And it's the first programmable machine. And the side note here is that Babbage and Turing have both proposed digital programmable machine concepts. Colossus is the first to implement it. Okay, well, what's the impact of having Colossus available at Bletchley Park? Well, the Operation Overlord depends on deception of the Germans. And so interception of the high command traffic allowed the commanders to observe that the deception had been confirmed, because they observed that the high command was believing that we were going to attack in a different place than we did. They learned the deposition of the German troops around Europe. They modified some of their parachute drops to avoid German gun emplacements. They decrypted Rommel's entire 50-page assessment of the German defense and tactics of Europe. And so they kind of got the game plan. And they learned that Rommel himself was kind of suspicious of the communications and felt like somebody was eavesdropping on them. And so he was right. And so following D-Day, of course, the Germans quickly modified the cipher on their main link and went to daily setting changes. And so it got harder, but Colossus was so programmable that it allowed the Allies to quickly recover their ability to decode. So what happened after VE Day in Europe? And so the production of the Colossus stopped after the victory in Europe Day, but the Japanese section at Bletchley continued until VJ Day, which is later. For security, the British decided that they didn't want anybody to know about Colossus, and so they destroyed everything. They basically destroyed the hardware and the documentation of the Colossus machine at Bletchley, and they only kept 2 of these Colossus machines around, stuck in some undisclosed location in London. So they didn't quite destroy everything, but they didn't want anybody to know what they had been doing. And I think particularly they're talking about the Russians at this point. Now, Alan Turing and others are involved with the Allies, after VE Day, to analyze what had happened over in Germany. And so what they learn is that the Germans' code-breaking activity had figured out how to break the British codes early in the war. They had monitored supposedly secure calls between Churchill and Roosevelt, and understanding that they were breaking speech communications. They were also working on speech encryption technology so that their analog or voice communications would be secure. At the end of the war, basically the head of Bletchley Park, this Edward Travis, is given the title KCMG, or Knight Commander of the British Empire, which I think is a great title. Turing and Newman, however, who basically did all the work, a significant amount of the work, were named officer of the British Empire. And Newman, for his part, declined. He thought it was an insult that they didn't name the guys that broke the code that saved them, something higher in the pecking order. And of course, Flowers, who is kind of the heart of the thing, is named member of the British Empire, which apparently is a lowly British title. And so, although it is a title. Okay, well, what happens to all these people at Bletchley Park after the war? This Max Newman, who had headed that department that built the Heath Robinson and then ultimately used Colossus, heads the Department of Mathematics at the University of Manchester. He put together a team to build the first stored program computer, which is called the Manchester Baby. And you can see a picture of that over on the right. There was just a milestone award, IEEE milestone award last year for this computer. And this computer was demonstrated in 1948. So the key development was the Williams tube, or electrostatic storage tube, which is the first random access memory. And so now we have an electronic storage device that can hold the program. Alan Turing, for his part, would join Newman at the University of Manchester in 1948 until his death in 1952. Turing's proteges at Bletchley Park, a guy named Donald Mitchie and Jack Good, they were Bletchley cyber analysts, continued Turing's machine intelligence work after Turing's death. And Mitchie then becomes the head of machine intelligence and perception at Manchester University and editor of a journal called Machine Intelligence. Good, for his part, is a faculty member at Manchester University and later moves to Trinity College in Oxford. Okay, well, here's what happens to Alan Turing after the war. Alan is not at Bletchley when the war ended. He's off at a place called Hanslope Park, and he's working on the British encryption of speech technology. And so, like the Germans, they're trying to figure out a way to encode speech communications. In October 45, Turing then joins a thing called the National Physical Lab in London. His goal is to build a child machine or a self-learning machine. I call it, it's an AI, basically. Turing would bring in Tommy Flowers and two members of his team at the post office Doris Hill Labs to work on his new machine, which he called the Automated Computing Machine, or ACE. The ACE development, however, didn't get off the ground very fast because Turing was playing with different concepts for the machine, and he basically didn't finalize the logic design. And increasing demands on Flowers at the Doris Hill Labs, or the post office labs, basically made it difficult for him to do much. And so this whole program, this National Physical Lab program, was canceled in March of 1946. In September of 47, then Turing basically is discouraged, goes back to Cambridge and begins writing a paper called Intelligent Machinery, his paper on the child machine, or the AI. In 1948, he joins Max Newman at Manchester University, where he continues his work in artificial intelligence. And then finally, in 1952, which is, I guess, 4 years later, he is arrested for gross indecency and forced to take hormone treatments. And so, as you recall, basically, this leads to his suicide in June 8th of 1954. Okay, well, here's the final postscript on this talk. Basically, in 1964, Stanley Kubrick, the famous movie maker, wrote a letter to Arthur C. Clarke asking him to collaborate on a really good science fiction movie. Jack Good, the Turing protege, he basically wrote a paper in 1965, of course, which is 10 years later, speculations on the first ultra-intelligence machine. And so Kubrick and Clarke are advised by Jack Good and Marvin Minsky of MIT on the movie 2001: A Space Odyssey. And so the close of this thing is HAL 9000 is born. And so you can see the artificial machine has matured. So that's my story. I'm going to unshare, and then maybe we can talk.
David, why do you think they kept Colossus a secret for so many years, for decades, I think?
Yeah, I think they wanted, I guess I would assume that they just didn't want the Russians to know what they were doing. I don't know why the technology would have been that super secret as you got into the 50s and 60s. But you know, that's kind of the way of the encryption community. They kind of keep things secret for a long time. And of course, I think I told you the story of UNIVAC. You know, how they were, you know, came out of the the cyber people, or I mean the code breakers from the Navy. Well, UNIVAC was basically run by, you know, the same guy that was running the code breakers became the I think his title was Deputy Director of the NSA, the National Security Agency of the United States, which is the code breaking operation. And so it continued to be part of UNIVAC for, you know, I don't know. They never told me. I didn't know that was what was happening, but basically parallel things. Yeah, there was a top secret type of program doing this kind of stuff, and then there was the main computer business that that I was involved in. So I never was really aware of that, but obviously they keep this kind of stuff secret.
Thank you.
Any other questions?
Yes, David. Hi. I would like did you hear me? Yeah.
Yes.
I would like to get back to this type of Enigma machine, German days. I would like to understand how really works, because you have a message in German, yeah? Message in German. You put this is the input of the machine. The output is another text in German also, but with some type of code inside. But you need to translate to a telegraph signer like dash and dash, dot dash, and then put in some frequency. But you need to know for each message in which frequency they are sending.
Right.
You cannot hear all frequencies. Which will be the frequency in which German works?
Well, I'm fairly simplistic on this. It seems like it had 12 wheels, and the size of the wheels varied. So, like, you know, in other words, and so you would get a different output from that wheel based upon its position, you know, where its starting position. Okay. And so it's kind of like a slot machine. You know, they spin all these wheels, and out would come some random number, you know, that, you know, that you put the code in, and out would come this random number. And so it's basically just a complicated pseudo random number generator. And they did that presumably on each of the 5 bits, you know, to get the new code. And you recall that the Germans started off by sending the key code, which is the settings at the front of the message. So initially they were able to kind of figure that out and strip that out and figure out how to set it up. So they're, you know, once they figured out how many wheels they had on each of those 12 wheels, you know, the number of positions and so forth, they could once they figured out the key, the settings, they could basically set up their hardware equivalent and then decode the message. But then the Germans got rid of sending the key along. So, you know, their people then knew, you know, had a list of these keys that they were using on a given day. And so then you had to legitimately decode all those wheels. And the only guy that figured out how to do that was this Tootie, who basically said, let's go count all the dots and create this code. And so we'll take a guess, they're basically going to take a guess, and we'll figure out which guess is the highest probability. And so that's how they statistically decoded which one is right. And so they ended up with that algorithm. And so then we just had to have a machine that would run fast enough. And so apparently, I actually don't quite know how all these coding things work. So I didn't analyze it too thoroughly, but particularly back in this idea of the pinches, where they were doing getting the code book and getting the physical machine and figuring out how to decipher all that stuff. And I don't know how all that worked, but it's so clearly we got a lot more than 12 wheels today when we're encoding and decoding things to the point where we got 100 and I can't remember some of the encryption length, number of different bytes or characters of encryption length that we do today. And so of course it's taking the fastest computer we can build, and then they're talking of course of decoding this stuff with quantum computing. And there's a terminology is post-quantum encryption, or in other words, how are you going to break the code if it's generated by a quantum computer? So that's where we're at today. Of course, is a lot of smart people working on that problem. And
okay.
And I would submit, and I don't know if you guys were aware that I did a talk with the IEEE USA. It's on YouTube. It's about the CHIP Act. So I don't know if you're aware of that CHIP Act, but U.S. is spending something like $52 billion this year to bring more manufacturing of chips back to the United States. And my part of that talk was basically reviewing the history of the development of supercomputers. So I kind of, because my first job was at Control Data, the supercomputer company in 1971. That was a transistor, discrete transistor computer. It was maybe the fifth or sixth generation of Seymour Cray's computers that he had designed in discrete transistors. And so that was the first one that I had any familiarity with. And then I get involved later on with a CDC spinout called ETA Systems. And so I was involved from Honeywell in helping provide the technology that they used in that supercomputer called ETA-10. And then, I've been involved in high-speed computer components. I'm more on the chip side and not on the system side, later in my career. But the conclusion of my talk was literally, I talked about how we've run out of scaling. We can't build chips any smaller. In other words, we have maybe another year or two before you can't scale the transistor too much smaller. It's called the end of Moore's Law, they call it. And, so it's all about beyond Moore, they call it, which is basically innovating packaging techniques. And so that's called 2.5D and 3D integration. And so I show pictures of the latest supercomputers that have been developed. There's the one called the Frontier. That's the current fastest one at Oak Ridge Labs in the United States. And it uses this very sophisticated 2 and 3D integration. And my conclusion was, number one, you got to have the chip technology and the packaging technology to build these things. And it's not so good if it's all overseas. And two, guess what? The prime application of that supercomputer is. I might suggest to you it's encryption and decryption.
Thank you.
Yeah, anyways, that's my...
Thank you, David. Thank you.
Yeah. Other questions?
David. Sorry, may you say again, where is that talk available?
Now, tell me again.
No, you said that talk is available somewhere. I don't
Oh,
know.
it's on YouTube. You could probably type in IEEE USA and then CHIP Act.
Okay.
You know, there was two parts to that talk. You know, Matt Francis, who's the Region 5 director elect, he's the guy that talked about the CHIP Act itself. He's involved directly. Me being retired, I just told the history up to this point. I was kind of projecting this vertical integration. You know, the name of my consulting firm is called Vertical Memory. You know, in 2002, when I formed that company, because I was out of work, you know, I had at the end of my job at Ramtron Enhanced Memory, basically I was looking at the technology at the time, and I said the only way this is going to work in the future is if we stack these chips vertically. And so I would envision this idea of you know, stacking of you know, back then 3 or 4 was a great thing, and people were doing it in the military. You know, there was some military technology back then that would build a chip like that, but since 2002, basically it's become mainstream. And so if you're familiar at all with the latest high-speed AI processors or GPUs, they all use a thing called high bandwidth memory, HBM. And it basically is a chip stack that can be as many as 12 chips high, sitting on top of each other. And we figured out how to basically bring all the signals out of that memory 1,000 bits wide. Okay, and so it's an incredible accomplishment. And that's how we build high-speed computers these days. So anyways, that's how, you know, that was my vision, and they basically did it. They're doing it.
Thank you very much, David. Thank you, everybody. Is there any other question? Okay, if not, I'm going to thank you again, David. I'm going to wish you have a very nice trip tomorrow. I know that he's going to France tomorrow to have a IEEE talk in France. Is that right?
That's right. I'm eager to meet all the people over there. Anyways, thank you all for inviting me again. I think you just need to figure out how to keep doing this. You know, in other words, find some new topics every month or so, and keep doing it. I think it's activating Region 9.
It's true. And thank you for helping us to do that. Okay.
Yep. Well, what I would, you know, of course, what you saw is me just doing a book review. And so it's almost that simple. You know, you just have to
It's
write.
very interesting book review. Very interesting.
Yeah, right. So you have to pick the right book. I mean, that's the same thing with Unsettled. You know, the last talk was basically a book review. And so it's me using somebody else's knowledge base, basically. So you can do that too. And then, of course, undoubtedly, there's lots of interesting things. You know, I assume that any life member that's got 35 plus years in our industry has got some interesting stories to tell. And so I'm betting money that each of you has got something interesting to tell the rest of us.
Some of the life members that are watching you right now, they gave a talk. Very interesting talk.
Yeah. Okay, well, thanks.
Okay, bye-bye, everybody.
Okay.
Bye-bye, David.
Bye,
Yeah.
David. Thank you.